Hello, everybody. Today we have a special guest talking about one of the hottest, or should be one of the hottest topics in the semiconductor and electronics world today: electronics design and design verification, the challenges, the opportunities, and the solutions that companies are having to come up with. My name is Bolaji Ojo, founder and managing editor of the Ojo Yoshida Report. My special guest today is Moshe Zuckerberg. Moshe is the CEO of Various. Moshe wears, different hats depending on which areas he's operating in, but he has been in this industry for quite a while, and he's a perfect person to talk with us about maybe the design world, the chip design world, the AI design world, and all of that. So let me just give an introduction to him. Moshe has more than 20 years of experience in the semiconductor and especially the EDA, the design automation world. He spent 12 years at Cadence Design Systems in various roles, including general manager of the Israel and European head of professional services. He founded Various Solutions, which is a leading ASIC services company. And like I said earlier on, Moshe wears several hats. He is a partner at Silicon Catalyst. He is exposed to a range of semiconductor projects and a variety of design and verification approaches. This is important to kind of lay out the background of why we're talking with Moshe, because the topic and the subject he wants to address now, it has always been important to this industry. It's increasingly important now. And the future of the semiconductor world is going to be defined by what happens in design verification, AI, and the entire chip world. Moshe, it's a pleasure to welcome you to this chat.
Well, Ajay, it's a pleasure to be with you today.
So I've set the stage. I've talked about your background. And that's important, like I said, because you can help us look back. What's happened in design world, what's going on now, and what you see in the years ahead. So let's start with that basic fundamental of the past today and what you see, kind of like your projections for the future.
So just to connect to your introduction, so indeed, I'm CEO of Various Solutions, which is a services company that we do different projects with customers and for customers, and therefore we see a wide range of different designs and different cultures even, and different applications, and et cetera, et cetera. I'm also a partner at Silicon Catalyst, where we actually see a lot of early stage companies doing different things in the space, in the semiconductor space. So I really want to tap into this, my past experience and the really wide range of applications and use cases that I'm seeing these days. So, it's not a secret. Now, to your question, it's not a secret that, chip design in general, it's increasingly complex. The chips are becoming bigger, more complex, more iteration between different functions, and et cetera, et cetera. That's true for the last, 20 years, or, it's increasingly going up, as the process nodes going down, the complexity is going up. But to some extent, things were relatively simple, and it's important to mention relatively simple in the SoC space, because what the industry has done with SoC is actually create a Lego approach of different IP blocks, where I have a CPU of some kind, an ARM or RISC-V. I have a bus or a NOC, that can connect different functions. I have a PCIe. I have a lot of predefined, pre-designed, pre-verified blocks that I put together. And in the SoC world, a lot of this became both on the design. There is always a little bit of new stuff to be designed and a new stuff to be verified. But a lot of it is putting together pre-designed and pre-verified blocks. And the challenge, which is still a challenge, but it's a challenge of a different kind, is to integrate these blocks on the design aspect, and to verify the integration, that everything was connected properly, and et cetera, et cetera. But it was not a big deal of from the scratch design and from the scratch architectures. The architectures were pretty much the same. or very similar with some variants, and sometimes you have this processor and that processor, and that I/O, depending whether you are in a data center environment, whether you are in an edge environment, whether you are in an automotive environment, you need to take care about power, you need to take care about security and safety and other things. And again, by all means, this is not a simple task, but the degrees of freedom are still and were relatively limited. What we see at the moment with all of the activity, and there is a lot of activity in the iChip accelerator domain, is changing that in a big way, okay?
Oh.
So you still have in every AI accelerator, you still have a PCIe interface of some kind. You have different kinds of memory, whether it's an HBM or it's a DDR or a combination, or on-chip SRAMs and et cetera, et cetera. But other than that, every single player in this market is creating something almost from scratch. Okay, so that changes the landscape on a big way.
Sorry, Moshe, why are they doing that? Why would you go from simple to complex? I mean, there must be reasons why these players, like you said, are doing this.
No, because it's a different structure, it's a different paradigm. It's not a von Neumann paradigm with a CPU that actually runs a lot of software in a centralized way, or you have maybe a multi-core, but still you have 2 cores, 4 cores. In a typical AI chip, whether it's a GPU based or a complete ASIC, you have a core that's designed from scratch to do usually multiply accelerators in some way and some shape or form. And the memory comes in, and how you're going to structure, how big is going to be your processor unit, how big is going to be your memory, where you put your memory, how much memory you put for every processor unit, and etc. It's a completely, many people are starting this from scratch. So from the very structured SoC bus-based, CPU-based structure and paradigm, you are in a completely different ball game, so to speak. Sometimes I tend to compare the AI landscape to, very simplistically, to a bowl of cereals. Okay, so everyone has a different size of the bowl of cereals. Some people have a smaller one, some people have a big one, and some people like more cereal, and some people like more milk, and any combination of the two. So the big attributes or characteristics of an AI chip is how big the chip is, how much processing or how many processing units you have, how much memory you have, where you have what. And that's why I compared this to a bowl of cereals. How much cereals you have, how much milk, and what's the combination between the two. Again, very simplistically. So you have people like Cerebras that they have a wafer size of an AI chip, and you have people that have a much smaller, and they can be connected. Well, it's hard to connect multiple bowls of cereal, so that's where my analogy fails. But some of them have memories here and memories there, and the processor unit may be they're usually another difference between my analogy, because the processing units are very similar and repeated, but sometimes you have some processing units that deal with out of order sequencing, and others that do ordered sequencing, and et cetera, et cetera. So you have it's a completely different ball game, because it's a different paradigm of computing. Okay.
What is the goal?
Go ahead.
Sorry, Moshe. The thing is this, if it's completely different and it varies by the design company or the customer, let me say, what are the goals? What makes that difference? What are the components that make it different from one design company to another? And I want to tack on something else to that question. What's the role of the EDA companies now in that process?
So again, why it's different, I think I explained, because it's a different problem that you're trying to solve. Okay, it's not a more or less ordered line of instructions that you are executing them one after the other, as you do in the von Neumann CPU paradigm. Here, it's a lot of things happening at the same time. Very often, these are systolic arrays moving, you know, each one moving the data to the next line and or the next element and et cetera, you know, both north and south and east and west and et cetera. So it's a completely different way of computation. It's a different way of getting the data in, out, and intermediate data. So you need, you know, indeed you need a different structure, and that's what people are playing with. And you know, you have different companies playing with different structures, as I said in my analogy to the cereal, to the bowl of cereal. Now, today you're asking what the EDA companies are doing with that. So I will tell you what the users are doing with the EDA companies or the EDA tools. So at the moment, people are trying their best to use the existing tools that were in most cases created to solve the SOC paradigm, okay? And they're trying to expand and stretch and try to use it in the AI world, okay? Now, what's different from the EDA perspective? What's different in the AI chips compared to the SOC paradigm, okay? So they are big. You know, the AI chips, you know, I use the Cerebras example, but that's true for many other, you know, the Google TPU chip is enormous, and all of the chips in the data center are big. Okay, Cerebras are taking this to the extreme, but all of the others are big, and they are using, most of them are leveraging chiplet structure to put together a combination of big chips. Each one is a big chip on their own. But you know, they are big, so they are hard to design, they are hard to verify, even if they are repetitive to some extent, but they are hard to design, hard to verify because of the massive number of space states and you know, the just sheer data that are needed to verify the chips. As I said, they are new. It's not just verifying the integration of previously designed blocks, but the blocks themselves are new. You have a lot of interaction. You know, in an SoC space, you have one CPU controlling mostly everything going on the chip. And here, everything is happening at the same time in every part of the chip. There's a lot of interaction that you need to check. There is a lot of very often there's a lot of coherency, you know, different people writing to the same memories and writing and reading from the same memories. Everything is happening at the same time. Okay, it's not a central control chip. It's a distributed computing paradigm. Okay, there is, and as part of it, there is a lot of hardware-software interaction as well. You know, very often, sometimes it's a real software, sometimes it's just a configuration, a register configuration of different processing elements, but everything is happening at the same time, and you have a lot of permutations, a lot of variants within the chip. So this is a different ball game in terms of the complexity for you know, the users, and by extension of the EDA companies as well. You know, here is you know, maybe that's a point. You know, I just mentioned what are the challenges in verifying AI chips. You know, maybe that's the right time to mention that are going to be in exactly a month from today, when we are recording this conversation, but it's, you know, check, I don't know exactly when you're going to be posting this. I'm actually organizing and moderating a panel at DVCon US in San Jose on the 26th of January. The conference is happening between 24 and 27, but the panel will take place on the 26th of February. And the topic is, why are AI chips harder to verify? Okay, so that's
the area that I wanted to dive into. You know, you've explained how complex it is. Before you go into how the processes of verification and the challenges that are there, let's talk about the professional landscape. You know, what you've described is a situation where you cannot have one single person, even within a company, have all of these complex experiences and skills to do that. So when you talk about the AI chip design and the current design environment, what are the skill sets that are required? That's number one. Number two, you know, do we really have enough of such, considering the explosive nature of the market as at this point?
So I can only partially answer your question because part of the you know, as I said, you know, I maybe explained why it's harder to verify, but the solutions to the problem are still evolving. So there might be new solutions and new skills that are needed. But having said that, let me answer your question. Again, the basic skills that you need to design and verify such chips in a good way, they're still the same. You know, people need to have a good understanding of the problem, a good understanding of the system. But as I said, you know, that now you are designing a much bigger part of the chip and not just reusing previous available blocks and elements. For verification people, you know, to try to understand, have a little bit of a detective mind to try to understand what can go wrong and try to test for these situations of what can go wrong. It's very important. But as I explained before, much more can go wrong because everything is new, everything is happening at the same time, and et cetera, et cetera. So this detective need to, you know, really understand the whole landscape. It's not just to look into one place. To debug such situations, it's much more complex because everything is happening at the same time all over the place. So you know, in terms of the intellectual skills, I think that's what I just said. You know, that's this kind of understanding of the big picture and the little details as well, and this kind of a mind to try to understand what can go wrong. That's what you need on the intellectual level. In terms of the technical skills, then it goes back to what I said in the beginning. You know, so in the past you would have, you know, a designer that will know Verilog and a design verification person that will know System Verilog usually. And here, because of the size, because of everything that I said before, because a lot of it's new, because of the activity, we may need much more of System C and C++, both for design, for verification. A lot of what happens in AI chips is that you have different representations of the data sets. So you have integers, you have floating points. You can sometimes, some companies invent their own representations of the data set, and which makes all of the design and verification much more complex. And very often you simulate this in C or MATLAB, and you want to verify afterwards. So again, this kind of things happen in the past in the communication systems and etc. But it's much more important these days. So, you know, the whole combination of hardware software is much more important these days. So in terms of technical skills, you know, the whole understanding of C, C++, System C may turn out, Python sometimes may turn out to be more important. And then there is a whole new thing in terms of AI tools that can help in the process of design and verification and implementing of these chips. But that's a whole new topic to discuss.
You said that the solutions are still emerging. Okay, so let's look at what are some of the current solutions and what are their shortcomings, if any, and what do you think? I mean, you've described it in so many ways, but let's first look at the current solutions that are coming up. I mean, you know, I'd like to see who's coming up with these solutions and what are the limitations and it seems to me every time there is a challenge, there is also an opportunity, right?
By all means.
Let's talk about that.
By all means. So again, as I mentioned before, currently people are using the solutions available in the market. To some extent, we are using today the solutions are available to solve the previous problems, so to speak, but we are trying to stretch them as much as possible, while new solutions, completely new solutions are defined and developed and et cetera, et cetera. That I'll come back to this later. I believe that once we develop new solutions for the new problem, we'll be able to use the new solutions also in the SoC designs and make them more efficient and et cetera, et cetera. But let's come back to this later. In terms of again, I mentioned the panel. I'm looking forward to hearing from the experts. You know, we have experts from different types of different companies and different types of companies. We have you know, people from AMD, which is, let's say, a big semiconductor company. We have a representative from Groq, who is a big startup company that raised hundreds of millions of dollars to put in place their ideas. We have a gentleman from Matix, which is a smaller and younger startup that is focused on AI chips for transformers specifically. And we have Harry Foster, who is chief verification technologist with Siemens and very well known, and he's a long time observer of the EDA industry and design and verification specifically. So I'm looking forward to hear what they have in mind as solutions. I can tell you, still I want to mention a few things. Emulation is increasingly being used. It's really stretching the boundaries of what is available because, as big as these machines are, they are very often expensive, and they are and the chips are bigger, so you can't really put the whole chip in an emulation, both from technical reasons or from money reasons. So you need to come up with all sorts of different tricks to map into and to have a representative subset in the emulation box. But that's definitely one way that people, or one technique people are using increasingly. Again, nothing new. It's just using this to the new type of chips. Formal verification is increasingly being used. Specifically, one area that we have a lot of experience here in Various too is using the different tools by different vendors for comparing a C representation of the design to the RTL. So there are different tools that do C to RTL or DPV comparisons. So these are critical these days, and we have a lot of good experience in this space. Especially because of the different numbering system that I mentioned before. This is very critical.
Okay. I wonder, can you mention some of the companies that you're using solutions from them? I mean, this is like, let's just state it out there. Which are those companies? I know you may not want to list them, but can you mention a few companies?
The EDA companies, you mean?
Yes.
No, I'm talking. I'm talking about the usual and very good, the usual suspects and very good partners. So, Cadence, Synopsys, Siemens. They lead the EDA industry. So they certainly are trying their best to extend what they have in terms of the current generation of tools, and try to add AI to these tools, etc. They are doing their best. I do see that there are newcomers disrupting, coming in, and I mentioned the DVCon, but I'm preparing a session. I did organize a session at DAC last year, DAC 2024 in San Francisco, where we discussed the usage of AI in chip design. And I'm preparing another session probably for DAC of this year about different companies, different startup companies coming with possibly disruptive tools that leverage AI to try to do things in a different way. Of course, the big EDA companies that I mentioned before, Cadence, Synopsys, and Siemens, previously known as Mentor, they have they have massive investments there. As we know in general, the innovator's dilemma. Sometimes Clayton Christensen, right? Sometimes being the incumbent is hard to fully innovate. So I am in touch and talking to some of the completely new startups, sometimes 2-3 people, sometimes 10 people, which are really, we see more and more of these guys appearing and trying to address the different points where, trying to do things in a different way because of the new possibilities that AI gives, but also because of the new challenges that, the AI both gives you new possibilities to try different things with LLMs and et cetera, but AI chips are also creating new challenges. So you have the two things, which that's the reason that I believe that we are in an inflection point, because we both have the possibilities created by AI, but we also have the challenges created by AI. So the two things actually, they can negatively impact each other, but hopefully they will positively. This drawing by Escher where you have the two hands drawing each other, right? So I believe that, and even I think Jason Huang in his speech at CES, he said that NVIDIA is using AI to develop the next generation and generations of new AI chips. So I think that we are in an inflection point that both the possibilities and the needs will create a new type or new types or new paradigms of chip design and verification and implementation tools that, again, may be able not just to solve the new challenges of AI chips, but will solve and make possible design and verify other types of chips in a different way, an easier way. Okay, that's what I believe.
It's interesting, Moshe, that you talked about AI being used to solve problems that AI did not create the problem, but the need for AI solutions is so vast that you do need AI in some ways to also solve problems that are related to AI opportunities, right?
No, so, what I mentioned before is that designing an AI chip did create some challenges. You know, we don't like to talk about problems. We like to talk about challenges.
Okay.
Because, you know, the difference between a problem and a challenge is that challenge is something that you come up in the morning to address them and to solve them. And that's what people are doing. So people are doing this by taking the existing tools and stretching them as much as possible, or trying to adapt, trying not to take the full chip. Let's put a representative set in an emulation and et cetera, et cetera. So that's one thing. And, but, as I said, there are newcomers trying to offer new solutions to the new problems. Okay. And if I may add to that, and which is also something fascinating, you mentioned my activities with Silicon Catalyst as well. As part of it, I'm also in touch with a lot of different VCs and investors that want to invest in semiconductors and et cetera, et cetera. In the past, you wouldn't see many VCs interested in the EDA market, which is, you have only 3 players as an exit strategy and et cetera, et cetera. Now, because of this inflection point, not just you have some crazy people that want to create new small EDA startups, but I'm seeing more and more investors and VCs that are interested in funding such startups, which is something completely new in the landscape, okay? Which, again, shows how much of an inflection point we are in.
See, I believe Synopsys is one of the big players in this segment. And I think I recall a conversation with the CEO where he mentioned the fact that not only do they now talk more and more with semiconductor companies, in fact, EDA companies are now even talking with, hyperscalers. They are reaching way deeper into the design chain than they ever used to. I'm assuming that this is a positive because then it engages the entire industry much earlier in that design process.
Well, it's not a secret that a big part of chip design today is done in the system companies, the exascalers, and et cetera, et cetera. So Synopsys and Cadence and Siemens are not just talking to them as, the customer. They're talking to them as the customer because,
Correct.
They are, again, it's public knowledge that all of, Apple, is doing their own chips. They're not buying, it's public. They don't advertise, let me put it this way. They advertise the new chips, the M1 and et cetera, or M, whatever it is at the moment. They advertise this when they launch a new laptop or a new phone. They advertise the chip as much as they advertise the end product. So it's not secret that Apple is investing heavily in chip design, and Meta, Facebook, and Google has 6 or more versions of the TPU. And Microsoft has the Maya chip, and Amazon is investing heavily in that. So they're all investing. Tesla, it's not just the exascalers. I don't think that Tesla qualifies as an exascaler. I think there are more than rumors that OpenAI is investing in a chip and et cetera, et cetera. And of course, you have the Sambanovas and Groks and et cetera, which are also becoming, all of this different the different categories that, you know, in the automotive space, you would call them the OEM tier 1, tier 2s. In the automotive space, they are becoming one to some extent. And certainly in the data center cloud space, they are becoming one because, you know, they are not, you don't have semiconductors selling to someone that is providing cloud services. You know, NVIDIA is providing cloud services to some extent. So all of those different silos are blurring. So by all means, the EDA players are speaking and should be speaking because that's what a lot of the discussions and the chip design is being done. Again, back to my DVCon panel. At the moment, I don't have an exascaler represented there. That might still change. I'm still considering that.
I hope so.
Because they may handle or address the problems in a different way. So we may have a representation of that. And if not in this time, in a future opportunity.
Correct. So Moshe, I have just a couple of questions more, and I want to go back to DVCon. Okay, the topic that you've chosen is the title of your panel that you're going to be having all of these guys at is are AI chips harder to verify? Now, that's the question you're going to be asking these folks. I'm going to preempt them by saying to you, Moshe, are AI chips harder to verify?
So again, I think I said they are. I think they are said that they are. They're certainly different. Okay, they're certainly different. And by different, you know, we say sometimes that you know, every kid is different. Okay, you know, to raise and to educate, whether it makes it harder or not, that's a different question. But they're certainly different. Okay, you know, you need to. Some of the tools that you use for SoCs can be applied and should be applied, but some of them needs to be applied, you know, with a twist, and very often you need new techniques and new tools to address the AI chips. But again, I'm very interested to hear what the guys have to say. So so I don't know, be there and let's see what they say. And again, I touched on this twice, so I want to get to this now. What I'm certain is that whatever solutions we come together for AI will come back and make our life different and, you know, possibly easy in other types of chips as well. So I was thinking, you know, it's a thought exercise. Okay, so you have a new problem. Initially, you use you know, whatever solutions you have for this problem. But gradually, you develop a new solution for the problem, okay? And once you develop a new solution for the new problem, the new solution can help you in the old problems as well.
Older problems, yeah.
Okay.
So in essence, and that brings me to my last question, which is, it seems to me that despite...
Let me, just before we go there, let me just give you another example of this that I think it's a fascinating example.
Okay.
When we had COVID, initially we tried to treat COVID with the old type of vaccines that take 15 years to develop. But then eventually people created the mRNA vaccines that in 10 months we had a new vaccine in the market, okay? And so we had, you know, the industry created a new tool to address a new challenge. And now, once we have proven that mRNA is a good way, we can use mRNA to solve cancers and other old. We don't need to spend 15 years to develop a new vaccine as we did in the past.
That's the interesting conclusion that I kind of got from your discussion so far. So, and it comes down, like I said, to my last question, which is, overall, despite the scale of the challenges, you are optimistic about the future of the design, the EDA side, the design process, and also the design verification part.
Oh, that's a yes or no question? Yes, I am. I am. You know, as I said, you know, because we are a services company and we work with different projects, different customers, and we solve different problems for different people, I'm seeing that the amount of innovation going on inside the companies, inside Veriest, inside different startups, inside the EDA players as well. So I'm very optimistic about us being able to address these challenges.
Any last comment, any last words? But well, definitely I want to encourage listeners to attend the DVCon event and also the panel that Moshe is going to be moderating. The title is Are AI Chips Harder to Verify? I mean, I think we've gone through a lot of things that show where the industry is leading. They may be harder to verify, but it seems to me that we are also hard at work trying to solve all of these problems. Any last words from you, Moshe?
No, it's, again, I think we covered it well. It was a great discussion. And again, all of this topics about design and verification and implementation and the software elements of different chips are, I'm very passionate about it.